Hi everyone. I'm Teng Guo, a PhD student at Rutgers University. I'm thrilled to introduce our paper titled Efficient Heuristics for Multi-Robot Path Planning in Crowded Environments, co-authored with my advisor, Professor Jingjin Yu. The presentation centers on multi-robot path planning, abbreviated as MRPP. In this scenario, we are tasked with coordinating multiple robots within a given graph, each possessing a distinct starting and ending point. During each time step, a robot can either move to an adjacent vertex or remain at its current location. The primary objective is to determine collision-free paths for all robots, guiding them from their initial positions to their respective destinations. Two fundamental types of inter-robot collisions must be avoided, including vertex collisions and edge collisions. Typically, two objectives are considered for minimization. The first is the make span. The second is the total arrival time. Multi-robot path planning finds wide-ranging applications in various real-world scenarios, such as warehouse automation, transportation, swarm robotics. Solving multi-robot path planning optimally has been proven to be NP-hard. Numerous algorithms have emerged to address the challenges posed by multi-robot path planning. These algorithms can be broadly categorized into two main types: optimal solvers and suboptimal solvers. Optimal solvers include reduction-based solvers, such as integer linear programming, and search-based solvers, such as conflict-based search. In response to this scalability challenge, fast suboptimal solvers have emerged, including bounded solvers like ECBS, EECBS, ICBS, and unbounded solvers like PIBT, DDM, push and swap. In our research, we delve into the impact of density and distribution on the efficacy of current solvers, recognizing that these factors can significantly escalate the complexity of problem solving. To address the challenges, we introduce two novel heuristics designed to effectively tackle such scenarios. We first delve into the challenging scenario of global density, where a large number of robots are randomly distributed, resulting in an average density ranging from 40% to 60%. In our research, we've observed that existing CBS-based methods struggle when confronted with these dense scenarios. The primary culprit behind this struggle is the strong correlation among robots in such environments. The potential for conflicts is exceptionally high. When CBS-like algorithms attempt to address a conflict by imposing constraints, they inadvertently create new conflicts with other robots. This leads to a troubling phenomenon, a stagnation in the number of conflicts. Overcoming this stagnation requires numerous iterations for the number of conflicts to gradually decrease, potentially extending the algorithm's runtime significantly. To tackle this issue head-on, we introduce a novel heuristic that combines data-driven techniques with the CBS algorithm. Specifically, when the number of conflicts reaches a point of stagnation and becomes sufficiently low, we leverage data-driven methods to resolve conflicts at a local level, allowing us to swiftly obtain a solution. This strategic approach aims to mitigate the challenges posed by dense scenarios, ultimately enhancing the efficiency and effectiveness of our multi-robot path planning algorithm. Consequently, the hybrid solver surpasses the success rate achieved by the conflict-based search algorithm. In contrast, when we compare it to the fast DDM algorithm, which directly addresses conflicts locally using data-driven techniques, the hybrid solver stands out for its superior solution quality. In our second scenario, we investigate the influence of robot distribution on system behavior. In what we term the locally dense scenario, the overall number of robots may not be exceedingly high, but they are densely clustered within a confined region. In such situations, we have observed that solving these instances can be significantly more formidable compared to evenly distributed scenarios. This increased complexity arises from the strong correlation among robots densely packed into a limited area, leading to a substantial surge in potential conflicts. To address this challenge, we introduce a second heuristic. Initially, we employ unlabeled MRPP algorithms to transform the initial start and goal states into intermediate instances that are somewhat less congested. Subsequently, we leverage a traditional MRPP solver to address these intermediate problems and attain a solution. The advantage here lies in the fact that the intermediate instances exhibit significantly reduced correlations among robots, allowing the conventional solver to swiftly resolve them. This, in turn, leads to substantial improvements in both runtime and success rates. Thanks for watching.